Hi everyone, this lesson is a quick introduction to some simple first order differential equations. So a differential equation is one like this, where it involves regular terms as well as a derivative. Because this is a first derivative, we would say this is a first order differential equation. Now sometimes more complicated ones will involve higher order derivatives, second derivatives, third derivatives, and so on. And they would be called second order differential equations, third order, etc. Now let's see how we would go about solving this. So we've been given dy dx equals this expression, and we've been told this additional little fact here, which we'll use later, that when x equals 1, then the value of y equals 3. That'll come along a bit later. So let's begin with our equation. Now I will immediately write this. We have 3x squared minus 5x plus 4 to the fourth power multiplied by 6x take 5. And instead of dy dx, I will move the dx to the opposite side of the equation. I'll separate the variables. This way, any variables of y, and in this case there's only a dy, an infinitesimal are on the left, and anything involving x is on the right. Now I will integrate both sides of the equation. The integral of, that's effectively the integral of 1 multiplied by dy is y. Now the integral on this side, sometimes these will be a bit more challenging. I notice here I really don't want to expand this to a fourth power and then multiply through by this term. I could, and I'd end up with an awful polynomial. There must be a better way, and I think there is. I notice that the derivative of the expression inside this bracket is 6x take 5, which is right there. That suggests to me that I could use the substitution method. So what if I let variable u equal 3x squared minus 5x plus 4. du dx would be 6x take 5. du over 6x take 5 would be dx. So my integral then becomes u to the fourth power. I still have 6x take 5 from the original, but when I substitute for dx, I have du over 6x take 5. So it simplifies down to be a nice integral after all. It's the integral of u to the fourth, du, which is u to the fifth over 5 plus a constant of integration. Now writing this with my original expression for u, it was 3x squared, oops, that was minus 5x, plus 4, all to the power 5 over 5 plus c. The point we've got to is called the general solution of that differential equation that we started with, because there's a whole family of answers. We just need a bit extra information to calculate c, and that's where I'm going to come back to here. This tells me that when x equals 1, y equals 3. So I will substitute this fact. So 3 equals, well, 3 by 1 squared is 3, minus 5 by 1 is 5, plus 4, all to the fifth power, over 5, plus c. So 3 would equal, now what's this? 3 take 5 is negative 2. Negative 2 plus 4 is 2. 2 to the fifth is 32 over 5 plus c. It looks like c equals 3 subtract 32 over 5. That's the same as 15 take 32 over 5, or negative 17 on 5. So the specific solution, not the general one this time, it's what we had there, with our constant added at the end. 3x squared, take 5x plus 4 all to the 5th power over 5 minus 17 over 5. That's the specific solution for that differential equation. So this illustrates a couple of important techniques. A differential equation is one where we have regular old variables as well as a derivative. A first order derivative is a first order differential equation. We solve them by separating the variables and integrating both sides. This gives us a point which we got to here, which we call the general solution, because we don't have the value for c. If we're lucky enough to have some initial and additional information, we can substitute into the general equation, calculate c, and then we write the specific solution for these. That's enough for now. A nice quick little introduction, and thanks for watching.